Good morning. We'll move to the second portion of the second module of Geotechnical Engineering 1, Permeability of Soil. Now the picture that you see to the top right corner here shows concrete as a material allowing water to pass through it. Now concrete is made up of aggregate matter and the cement paste, which when hardened will give you a material like this, hardened concrete. So this picture says that when water is allowed to pass through it, the void spaces will act as a passage for water to pass, right? Concrete as a material is porous. It has got pore spaces in between the aggregate matter. So these pore spaces, when interconnected, will make the material as permeable. Had the pore spaces been not interconnected, water would just stay in those pores at the top portion and it will not be allowed to pass through it. So the interconnected pore spaces will act as a pathway for the water, or in general any fluid and material, to pass through it. So a material is porous if it contains pores, and it's permeable if these pores are interconnected. So just like concrete, soil is also permeable. And permeability, by definition, is the ease with which fluid can flow through a material. When water tries to enter the material, the soil, there will be void spaces in between the aggregate and the soil particles. So these pathways will allow water to pass through them, and depending on the void spaces and the pathway created, you have high permeable soil and low permeable soil, etc., depending on various features, which includes the diameter of the particles, but not just limited to the diameter. We'll have a discussion on the various features which influence the permeability later down the line. So in general, soil as a material is permeable and it allows water to pass through it. Now Bernoulli's theorem, you would be familiar with the Bernoulli's theorem, right? It says that the total head at any point of a flowing fluid or liquid is the sum of elevation head, pressure head, and velocity head. Now there comes a term called hydraulic gradient. Again, you are familiar with that. It's the head per unit length of the flow. Now Bernoulli's theorem would be applicable to any mechanics of fluids and in soil mechanics as well to a certain extent, except for the fact that in soil mechanics we rarely accommodate for velocity head, because the velocity with which water passes through the soil grains are very negligible, and what predominates is elevation head and pressure head. So hydraulic gradient, like we discussed, is I, represented as I, is equal to head causing flow per unit length of flow, I equal to H by L. Now the one law that helps us to arrive at the permeability of soil is Darcy's law. Darcy stated that for a laminar flow in homogeneous soil, the velocity of flow V is directly proportional to the hydraulic gradient H by L, or hydraulic gradient I. So velocity flow is proportional to hydraulic gradient, which means V is proportional to I. We have a constant of proportionality, K, there, which is a coefficient of permeability. V equal to K multiplied by I. V is the velocity, I is the hydraulic gradient, K is the coefficient of permeability. Now when you talk about another term, discharge, usually represented by Q, is the volume flowed per unit time. When you talk about the discharge of a pipe, the one that you use in your wash basins or perhaps in your lawn area, etc., the discharge is volume of water flowed per unit time. It's also a product of velocity and the cross-sectional area. So Q is equal to A into V, area multiplied by velocity. Now velocity, as per the first equation, is K multiplied by I. So in short, discharge Q is K multiplied by I multiplied by A, where K is a coefficient of permeability, I is the hydraulic gradient, and A is the cross-sectional area. Now we have a few factors which affect the permeability. I list these factors. Of course, the flow of water through soil is what we are discussing. So obviously you will have two broad terms. One is the soil property and the second one is water property. The soil properties include, but not just limited to, particle size, soil structure, particle shape, void ratio, etc. Whereas properties of water includes unit weight, viscosity, not just limited to these two, but there are others as well. So in general, particle size, soil structure, particle shape, void ratio, etc. and unit weight and viscosity are few factors which affect permeability of water through soil. Now, how to arrive at the K, or coefficient of permeability? K was defined in the previous equation. K is the one that connects velocity and hydraulic gradient. So K, the coefficient of permeability, can be obtained from field as well as in laboratory tests. Pumping test and pump out tests are examples of field tests which can be resorted to determine the K value. Whereas in lab, you usually go for constant head test and variable head test. It's not limited to these two, but the syllabus that we follow just demands us to explain these two texts. First one, constant head permeability test. As the name suggests, the head at which the water level is maintained remains constant. So it's conducted relatively for more relatively more permeable soil, like for instance sand, and it's not popular in case of clay. So the basic idea is quite simple. You have a container or a tank where there's a provision for you to maintain the head causing flow to be constant. So that's a constant head level there, and water is allowed to pass through the soil, and the quantity of water is collected in a graduated flask or a measuring cylinder. Now the discharge of this system is measured in this graduated flask, and the length of flow, area of cross-sectional flow, and H, hydraulic head, can be estimated. So in short, knowing length of flow, area of cross-section, and the head causing flow, and based on the discharge that you collect, that is volume per unit time, you can actually get the coefficient of permeability, because Q is equal to KIA, or Q equal to K multiplied by H by L multiplied by A, or when rearranged, it gives you K, the coefficient of permeability, which is the one that we are interested in, equal to Q, the discharge, multiplied by L, the length of flow, by A, cross-sectional area of the sample, and H, head causing flow. Now the procedure is quite simple. In the laboratory, like I said, you'll have a tank, a water container, in which the level of water is maintained constant. It doesn't fluctuate as the experiment progresses. The soil sample is sandwiched between two porous discs in what is called as a permeameter. So the typical diameter of this permeameter is 10 centimeters, and typical soil sample height is about 12.7 centimeters, approximately making the volume to be 1 liters, or approximately 998 cc's. So this is a soil sample above which you have a filter paper kept and a porous disc kept. Likewise below you have a filter paper and a porous disc, and the top cap is connected through a pipe to the constant head tank, and in the bottom you have a valve through which you can collect the water to a graduated jar. So the flow of water is quite simple. From the constant head tank, the water flows downward. It passes through the valve at the top of the cap, moves through the porous disc to the filter paper, and it moves through the length L of the sample all the way down to the filter paper, then to the porous disc, and it exits towards the graduated disc. So fundamentally, you will be given with a stopwatch, and you can measure the time taken for the volume of water collected in the graduated disc. So knowing the volume and time, you'll get the discharge. L is the length of flow, which is nothing but the height of the sample. H is the head causing flow, which is marked here. H is the level difference between the water level at the constant head tank and the point of exit of the water, which is the level of the valve here. So the difference in height between the valve here and the constant head tank's water level is H. So the procedure: soil from the field is filled in this permeameter in the field density. It is fully saturated by allowing water to pass through it and by ensuring the removal of air. You have a mechanism called as an air release valve here, which will help you to make sure that the sample that you've collected here is totally saturated. So if there is any volume of air left in the sample, you will allow it to pass through the air release valve. Now the constant head tank is then connected. This is a constant head tank. It is then connected to the permeameter's cap, and water is allowed to flow through it. The head causing flow, H, is noted. A stopwatch is started, and the water flowing out from the permeameter is collected in a measuring flask for a specific time to get the discharge. So you calculate the discharge based on the volume of water collected and the time taken to collect the volume, from which you will get small letter Q, or discharge. And knowing the cross-sectional area of the sample and the length of flow, you can get what is called as a coefficient of permeability, K. The cross-sectional area is nothing but pi d square by 4, because you have a cylindrical sample here. So you have the diameter, you'll get the cross-sectional area A, you have the length of flow, you have head difference or the height of flow here, and you have the discharge in centimeter cube per second or meter cube per second, depending on the consistency of the unit that you are interested in. So knowing all those things, you can arrive at the coefficient of permeability using a constant head test. Now this particular test is suitable just for the soil which has got relatively high permeability, or else what happens is that the volume of water collected in a particular time will be very low for you to measure. So that is where you resort to the falling head test. So falling head test, the one that we are about to discuss now, is suitable for relatively low permeable soil. Falling head test or variable head test. As the name suggests, the water head is not maintained constant. Instead, it's allowed to fall or vary. So it doesn't have a constant head tank. Instead, it has what is called as a standpipe. Now the standpipe is connected to the top of the permeameter, and the second difference is that you don't measure the discharge. You don't measure the collected volume of water. Instead, what you do is you measure the time taken for a height h1 to fall to a height h2. So this, like I said, is for relatively less permeable soil, for example clayey soil, where the volume of water collected in the measuring cylinder may be very low. Hence, in this test, the basic ideas are: the system is very similar to the constant head test, but the head crossing flow is allowed to vary with time. Second difference is that the discharge is not collected in a measuring flask. Instead, what you do is the fall of height and the time taken for this fall in height is measured. Now, the volume of water passed through the sand pipe is equal to the volume of water passed through the specimen and will be equal to the volume of water passes through the outlet pipe. So this is a basic idea. So let's assume that you have a standpipe of cross-sectional area A, small letter a, and you have the specimen sample whose cross-sectional area is capital A. L is the length of flow through the specimen. So when height or head coursing flow falls from H1 to H2, the volume of water in this zone will be passed through the specimen sample. This is a basic idea. So based on that, the equation that gives the coefficient of permeability is 2.303 AL by AT log H1 by H2, where small letter a is the area of standpipe, capital letter A is the area of the soil sample, L is the length of travel of water, and T is the time taken for the height to fall from H1 and H2. There's an editing mistake here. This is small letter t as per this equation. The derivation of this particular equation is quite simple. The basic idea is given here. Based on this basic idea, you can actually integrate to get the volume, and 2.303 is a term that you get when you convert the log scales.